Okay, we will take in this class the topic refractive index. See, we have studied that light is an electromagnetic wave and it travels with a speed of 3 into 10 raised to the power 8 meter per second. Nearly this, slightly less than this in vacuum. In air, the speed is slightly less than this, but the difference is too small that we take it 3 into 10 raised to power 8 meter per second in vacuum as well as in air. Now this is the maximum speed of light. Whenever light enters into a medium, the speed decreases. For example, if I take air and water and a light ray. In air, the speed is 3 into 10 raised to power 8, but as it enters into water, the speed here is less than the speed of light in air or vacuum. Refractive index is a quantity that tells the fraction by which the velocity or the speed changes. If this medium has a refractive index of 2, it means the speed will be reduced to half. That is the meaning of refractive index, and it is defined as, we use n, mu or eta to denote it. It is C by V. The speed of light in vacuum or air upon speed of light in the given medium, C by V. This is the refractive index. So refractive index is always with respect to a given medium. Whenever we are talking about the absolute refractive index, it simply means basically with respect to vacuum. So absolute refractive index, for example, if I say for water the refractive index is 4 by 3, it means this 4 by 3 is with respect to vacuum. If glass has refractive index 1.5, it means this refractive index of 1.5 is with respect to vacuum. And the way to write it, n refractive index of water with respect to air. This is how we write it. Or some books write it like this: refractive index of water with respect to air. Or even some books write like this: refractive index of water with respect to air. And we have seen now, refractive index of water with respect to air means speed of light in air divided by speed of light in water. Speed of light in water and speed of light in air. This is the meaning of it. This is how we represent it. Now, if I take refractive index of air with respect to water, what will it mean? It will be just the reciprocal of it. Okay. Same way, refractive index of glass with respect to water. What will it mean? Speed of light in water upon speed of light in glass. This is just opposite of refractive index is inversely proportional to the velocity. Okay. And refractive index of water with respect to glass. How can we write it? This is refractive index of glass with respect to water. is velocity in water, velocity in glass. Water with respect to glass will be velocity in water, velocity in glass. If I multiply these two, refractive index of glass with respect to water, refractive index of water with respect to glass, it is 1. So it means refractive index of glass with respect to water is reciprocal of this. This is how we represent it. Now, if there are 3 mediums, we have, say, air, we have glass, and we have water too. And I want to write refractive index of glass with respect to water. Then it is refractive index of glass upon refractive index of water. And whenever I am saying refractive index of glass, I told you that refractive index is always with respect to some medium. And whenever I am saying refractive index of glass, it means it is with respect to vacuum or air. So I can also write like this. So refractive index of glass with respect to water is refractive index of glass upon refractive index of water. This is how we represent the refractive indexes of different mediums. Okay, now the factors on which this refractive index depends. We have seen that it depends on the medium. So refractive index of glass is different from the refractive index of water. It also depends on surrounding medium. Surrounding medium, because refractive index of glass with respect to water is different from refractive index of glass with respect to air. It will also depend on temperature. See, when we increase the temperature of the medium, the density changes. Most of the substances, they expand on heating. So the intermolecular distance increases. Light can move faster now, or refractive index is reduced. So with increase in temperature, refractive index decreases. It also depends on wavelength. So refractive index is different for different wavelengths, and there is a relation for it. We call it Cauchy relation, A plus B by lambda square plus C by lambda 4 and so on. A, B, C all depends on the medium. So see now, higher refractive index is for lower wavelengths. For higher wavelengths, refractive index is less. Red has maximum wavelength. It means refractive index of any medium will be minimum for red and maximum for violet. So refractive index of any medium, maximum for violet, minimum for red. Okay. Briefly again, refractive index is C by V, speed of light in vacuum to the speed of light in the medium. This is the refractive index of that particular medium with respect to vacuum or air. Right? So whenever we say refractive index of, this is for water, this is for glass usually, and this is with respect to vacuum or air. This is how we write it: refractive index of water with respect to air, or water with respect to air, or water with respect to air, like this. And then I told you the reversibility of light, it's a property. So if refractive index of water with respect to air, we take the reciprocal of it. the product of the refractive index will be 1. Refractive index of glass with respect to water into refractive index of water with respect to glass, this is 1. Okay, and we can work it out using this velocity concept. For 3 mediums involved, this is how we can write it. Refractive index of glass with respect to water. It is glass upon water, both taken with respect to air or vacuum. Now, the factors on which the refractive index depends, it depends on the medium of which we are calculating, it depends on the surrounding mediums, it depends on the temperature, it depends on the wavelength. Increase in temperature reduces the value of the refractive index, and wavelength, higher wavelength means lower value of refractive index. Okay, now let me start another topic, refraction of light. See, whenever light falls on a surface separating two mediums, it may bounce back, it may be absorbed by the medium, or it may simply pass through the other medium. It is medium 1. Now I will take the refractive index. Medium 1 refractive index N1, medium 2 refractive index 2, both with respect to air. Okay, now if the light ray just passes through the other medium, we call it refraction. But in refraction, if the mediums are different, the speed of light is different. Here the speed of light may be, say, V1, then here it will be V2. And due to this different speeds in two different mediums, the light ray doesn't go straight. It bends from its path. It either comes towards the normal or it moves away from the normal. This is, we can again call it incident ray. This is the normal incident ray, and now the light ray, while coming to this medium, this will either comes closer to this or move away. If N2 is greater than N1, so I can say such mediums are called denser medium. So N2 higher refractive index than N1, it means second medium is denser. Light ray will travel slower in this medium. So the light ray bends towards the normal. This will be called the angle of refraction. This is the angle of incidence. If the second medium is rarer, it will come like this. And why this ray bends, there is a principle, we call it Fermat's principle actually. I'm giving you an idea why the ray of light changes its path. See, light has a tendency that in moving from point 1 to point 2, say from here to here, it will take a path in which time taken is least. So now I'm giving you two options. One is this and another one is this. Let me call this as path 1 and this as path 2. So in which case the light will take less time to reach B from A. See, light is traveling faster in medium 1 because it is rarer, it is denser. So it means light travels faster here and slower here. So if more length of path is to be covered in this medium, it will take more time. So this path will ensure lesser time than this one, because in this case it is covering more length in a rarer medium which it can cover quickly, and here it gets slower. If it takes this path, more length of the path is to be covered in a denser medium, so this will have to be covered in a longer time. So this is the reason why light changes its path in moving from one medium to another. And there are again definite laws relating the angle of incidence and angle of refraction. This is normal. Incident ray. This is the angle of incidence. This is the refracted ray, and this is the angle of refraction. Laws of refraction. First one, it says that incident ray, normal and refracted ray, they all lie in the same plane, just like the law of reflection. And the second one, it is also called Snell's law. Sine of angle of incidence divided by the sine of the angle of refraction. It is a constant for given pair of mediums. It is n to 1. Refractive index of second medium with respect to first. I will elaborate it further. Sin I upon sin R is n to 1, or n2 upon n1, or v1 by v2. This is Snell's law. The ratio of sine of the incidence angle and sine of the angle of refraction is constant for a given pair of medium, and this constant we call it refractive index of second medium with respect to first medium. In terms of velocity, we can write this. In terms of absolute values of refractive index, I can even write it n2 upon n1. Right? So I can even write n1 sine I is equal to n2 sine R. Refractive index of first medium, angle of incidence, refractive index of second medium, and angle of refraction.